Good morning, students. So today we start with the new chapter, that is electrostatic, potential, and capacitance. So marks allotted for this chapter is 8 marks, right? So one question will come for 3 marks, and one question will come for 5 marks, right? So these 5 marks either may be theory or problem, right? So very important topic. So this one is the continued topic as we discussed about the previous chapter, that is electrostatics, right? So here also we are going to discuss the charges which are at rest, right? So that concept is potential. So before going to discuss about the electrostatic potential, so let's recall some concepts as we already discussed in class level, that is conservative forces, right? So by considering one example, so a block is connected to the spring, right? So we already discussed about the kinetic energy and potential energy, right? So when an external force is applied to this block, right? So this one is the external force. When we apply the external forces to the block which is connected to the spring, so what happens to this block? So this block will displace. So right? So it changes its position from, that means small position, right? So the applied force is a external force, right? So when a block which is attached to the spring, which is applied by the external force, so whenever we apply the external force to this block, so this block changes its position, right? So that one we call as the displacement. So it changes from initial point. Here is the final point. So this is against the force, that one which has in the spring, right? So that one is the spring constant, that is the force due to the spring, right? So when we remove this external force, right? So this is the first case. What happens when the external force is applied to this block? So this block gets displaced against the spring force, right? So after, when it reaches here, the force which are applied on this block is stored in the form of potential energy, right? So ಯಾವುದಾದ್ರು ಒಂದು ಬ್ಲಾಕ್ಗೆ ನಾವು ಫೋರ್ಸ್ ಅಪ್ಲೈ ಮಾಡಿದಾಗ ಏನಾಗುತ್ತೆ, it displaces from its position, right? So that force is converted in the form of the potential energy. So applied force ಯಾವುದಕ್ಕೆ opposite ಇರುತ್ತೆ? So that force is the spring force. So that one we call as the spring constant, as we discussed this in the last class, that is in the class level, right? So now when we remove this external force, so what happens? Again these blocks will displace from here to here. So the blocks move from opposite direction, that is due to the force which is present in the spring, right? So here what happens when we apply the force? So force apply ಮಾಡ್ತಾ ಇದೀವಿ, object ಏನಾಗ್ತಿದೆ, displace ಆಗ್ತಿದೆ. So that one we call as the work done. So work is done, right? So we know the formula for the work done, that is force into displacement, right? So now force apply ಮಾಡ್ತಾ ಇದೀವಿ, object ಏನಾಗ್ತಿದೆ, displace ಆಗ್ತಿದೆ, right? So here we have the force and also the displacement. So ನಾವು ಅದನ್ನ ಏನಂತ ಕರಿತೀವಿ, work done, right? So this is the work done which is opposite to that of the spring force. So ಅದನ್ನು ಕೂಡ ನಾವು ಕರಿತೀವಿ, this one is the external force. So here we have the two work done, right? So work done due to external force, right? So that is equals to force external into the displacement we taken dx. So one more work is there. So that work is the work done due to the spring, right? So here due to this spring force, the force is F spring, but the displacement is minus dx, right? So the force of the spring is in this direction, but the displacement is opposite to the direction of the spring force. As we know, the displacement is also a vector quantity, right? So force is in this direction and displacement is opposite. So we know work done formula W is equals to Fs cos theta, right? So if both are in the same direction, then theta is 0, we get positive work done, right? So here force is in this direction and displacement is opposite to that of the force. That means theta is 180 degree, right? So we get the force that is minus Fs, negative work done, right? So this is the first case. So one more case. So considering this one as ground, we are lifting an object from the ground, right? So here we have the object. So by applying the force, external force, we are lifting the object for some height h. So we are lifting the object against the force of gravity, right? So here also we are applying the force, displacement happens, right? So F external is equals to, so here, sorry, work external is equals to force external into height. We get the positive value. So if we find the work done due to gravity, that is equals to minus F gravity into height, right? So here also we getting the two work done. So one is positive work done, another is the negative work done, right? So here this is stored in the form of potential energy, right? So here also it's stored in the form of potential energy. When we remove the external force, so ಇಲ್ಲಿ ಕೂಡ ನಾವು force apply ಮಾಡ್ತೀವಿ. When we remove this external force, what happens? It again comes back to the ground, right? So that means it changes from potential energy to kinetic energy, right? So that means the net or sum of potential energy and kinetic energy is conserved, right? So the sum of potential energy and kinetic energy is conserved. That means the total energy of this system is 0, because here one is positive value and another one is negative value. So sum of these two energies is 0, right? So the same concept here we are going to apply in case of the electrostatic, right? So from the electrostatic Coulomb's law, we have the positive charge plus Q, and here we have either plus Q or minus Q, right? So these two charges are also conserved. That means Coulomb force is conserved, right? So here in these two cases, it depends on only the initial point and final point, right? So the displacement we are considering only the initial point and final point. Here also we are considering the initial point and final point. We are not considering on the path in which we are applying the, that means displacing the object, right? So here the Coulomb force is conserved, and the next point is it is path independent. Right? So these are the 2 points, right? So Coulomb force is conserved in nature, and this Coulomb force is path independent, right? So we are going to discuss the same concept in by applying here in Coulomb's force, right? So we have the force, so we need to find the work done by applying the same concept, right? Right. So for that, consider a point charge or some charge Q, that is plus Q at origin, right? So placing this object charge is at origin, right? So next, consider one more charge at some point P here. So that one we taken as Q naught, right? So now we need to find the work done. So work done is if we have the charge here, so there is a space around this charge, that one we call as electric field, right? So electric field is in this direction, and if we have the electric field, again we have the force, so that force is the Coulomb force, or we call this one as the force, right? So next, we are bringing the charge from point P to somewhere here at the point R, right? So we are bringing the charge from point P to the point R. So this becomes the displacement. So how it will come from P to R, right? So we are going to bring this charge from P to R. So here we have the charge Q, right? So this charge Q has the electric field E and the force F, right? So this force, if this charge is positive, then there will be a repulsive force, right? So the condition for here is the Q and Q naught must be positive, or Q on Q naught must be negative, because these two may be positive or these two may be negative. We need the repulsive force, right? So the first condition is this one. These two charges either may be positive, either may be negative, right? So next, we need to bring this charge from P to R. So as we discussed in the last session, that is, if we apply the force, then only this object will displace, right? So in the same case here also, we are applying some external force, right? So we are applying the external force to this point charge Q naught. So then only it will displace from Q naught, that is from point P to R. So this external force is in such a way that it must be balanced the Coulomb's force, right? So external force is almost equals to the Coulomb's force, right? So that is F E or Fc. So this is force due to the electric field, right? So are you understanding this one? We have considered one charge here. So again we considered one another charge, because we are going to find out the work done. So we are moving this charge Q naught from point P to R, right? So when it will move from P to R, when we apply the external force. So now ಯಾವಾಗ external force apply ಮಾಡ್ತೀವೋ ಅವಾಗ ಮಾತ್ರ ಇದೇನಾಗುತ್ತೆ, ಚಾರ್ಜ್ from P to R ಗೆ ಮೂವ್ ಆಗುತ್ತೆ. So ಈ ಫೋರ್ಸ್ ನಮಗೆ ಯಾವ ತರ ಇರಬೇಕು? So this force is to balance this repulsive force, right? So Coulomb's law ಏನು ಹೇಳುತ್ತೆ? If we have two charges, this charge acts the force on the another charge, and this charge will apply the force on this charge, right? So these are equal and opposite charges, right? So ಇಲ್ಲಿ ತೋರಿಸಿರೋ ಕಂಡೀಷನ್ ಯಾವ ತರ ಇರಬೇಕು? This Q naught will not affect this charge Q. So that means Q is, that is Q naught is very small, right? That means it will not affect the original configuration, right? So ಇಲ್ಲಿ ನಮಗೆ ಈ ಚಾರ್ಜ್ ಇಂದ ಅಪ್ಲೈ ಆಗ್ತಿರೋ ಫೋರ್ಸ್ ಇದ್ರ ಮೇಲೆ ಯಾವುದೇ ತರಹದ ಅಫೆಕ್ಟ್ ಆಗಬಾರದು, ಬಿಕಾಸ್ ಇಟ್ ಈಸ್ ಅಟ್ ದಿ ಆರಿಜಿನ್, ರೈಟ್? ಸೊ ಈ ಚಾರ್ಜ್ ಮೇಲೆ ನಾವು ಫೋರ್ಸ್ ಅಪ್ಲೈ ಮಾಡ್ತಿದೀವಿ, ಈ ಫೋರ್ಸ್ ಯಾವ್ದಕ್ಕೆ ಈಕ್ವಲ್ ಆಗಿರಬೇಕು? ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಫೋರ್ಸ್ ಗೆ ಈಕ್ವಲ್ ಆಗಿರಬೇಕು, right? So but the applied force is from left to right. So here the external force we are applying from right to left. So these two forces are opposite, right? So that means F external is equals to minus Fe, right? Because these two forces are opposite, so that's why F external is equals to minus Fe. So iವಾಗ ಏನಾಗುತ್ತೆ? This charge will displace from P to R. So that distance we are going to take some dx, right? Small displacement dx. So ಇಲ್ಲಿ small displacement ಆಗ್ತಿದೆ ಅಂದ್ರೆ ನಮಗೆ ಏನು ಸಿಗುತ್ತೆ? Small work done, dw, right? So small work done is equals to the force into displacement, right? So here the applied force is the external force and we are getting the displacement, right? So dw is equals to F external into, so displacement dx. So by applying this force we are moving the charge from P to Q, so it displaces value the dx. So we get the small displacement. So we need the work done to bring this point to somewhere here, right? So that gives what? The total work done, right? So for the total work done or dW, so we are replacing this external force by the electric field. So F external is equals to minus Fe into dx, right? So for the total work done, we are going to integrate this value, then only we get the total work done, right? So W is equals to minus Fe into dx, right? So W is equals to minus Fe dx. So this gives the work done, right? So as this work done from here to here, it reaches, then it stores as the potential energy, right? So yaವಾಗ ನಮಗೆ ಚಾರ್ಜ್ ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಮೂವ್ ಆಗುತ್ತೋ that means it completely converts the force in terms of the energy, right? So this work done we call that one as the potential energy. After when we remove this extra to the repulsive force of this charge, so this charge will move away from the charge q. So as the kinetic energy is equal to work done, right? So we need to find this work done, right? So that gives what? Electrostatic potential, right? So first we define the potential energy. Right? So potential energy or electrostatic potential energy, right? So electrostatic potential energy is defined as electrostatic potential energy of a charge q at a point p in an external field is the work done in bringing the charge from infinity to that point without acceleration. Right? So this is the definition of the electrostatic energy. So that means here we have the charge q, right? We need to find the electrostatic potential at somewhere point here. It is at a distance r, right? So how we define the electrostatic potential energy is by bringing the charge from infinity to this point, right? So opposite to that of the electric field, right, or electric force. So that one we states as the electrostatic potential energy, right? So electrostatic potential energy of a charge q at a point p is the external. So in the external field is the work done. So work done is bringing the charge from infinity to the point p. So we don't know from where we are bringing the charge. So that's why we have taken that as the infinity. So from the infinity to this point, right? So without acceleration. So without acceleration is nothing but net force is 0, right? So we know F is equals to ma. If F is 0, that is net force is 0, then acceleration is 0 without acceleration. So acceleration is 0 means velocity is constant. So this velocity is infinitesimally small. So we are bringing the charge that is from infinity to the point p in a small speed or in a small velocity, right? So we call as electrostatic potential, that is electrostatic potential energy, right? So here one more we have electrostatic potential, right? So here we have the force due to the electric field Fe is equals to, we know, Q into E, right? So and also we know the work done. So work done is directly proportional, that is work done is equals to force into displacement, right? Work done is equals to force into displacement. So we know the force W is equals to QE into displacement, right? So here the electric field is constant and displacement is constant. So we can relate W is directly proportional to Q, right? So if we shift this Q to the LHS, then W divided by Q is equals to constant, right? So this constant we considered as electrostatic potential. So new term introduced here. So that one we call as the electrostatic potential. That means work done per unit charge we call as electrostatic potential. So and this electrostatic potential is denoted by V, right? So electrostatic potential is defined as work done per unit charge, right? So work done per unit charge, or in the same, the electrostatic potential of a charge Q at a point P in an external field is the work done in bringing the unit charge. So here we need to change bringing the unit charge from infinity to that point, right? So this gives what? Electrostatic potential, right? So electrostatic potential is defined as electrostatic potential at a point, electrostatic potential of a charge Q at a point P in an external field is the work done in bringing the unit charge. So this is the difference in between the electrostatic potential energy and electrostatic potential. So in electrostatic potential energy we are bringing the charge. So it may be of the any value, right? So in electrostatic potential we are bringing the charge, that value is equals to 1 coulomb. So that one we call as unit charge, right? So in mathematical form, if we return for the electrostatic potential, that is V is equals to W divided by Q. Or simply we can say work done per unit charge. So unit charge is 1 coulomb, right? So this one is joule per coulomb. So SI unit of the potential is joule per coulomb, right? So electrostatic potential is defined as work done per unit charge. So per unit charge is nothing but, unit is nothing but 1 coulomb, right? So now we going to derive the electrostatic potential relation, right? So there is a difference between the electrostatic potential and potential energy. So in potential energy we are bringing the charge Q. So here we are bringing the charge 1 coulomb, right? So for that, consider a charge Q at origin. So plus charge at origin, right? So we are going to find the electric potential at a point P, which is at a distance R. We are going to find the electric potential P at a distance R, right? So we know the definition of the electric potential. That means we are bringing 1 coulomb of charge from infinity. So somewhere here we are bringing this charge from infinity to this point P, right? So we are going to derive that one. So considering a point A, so that is at a distance x, right? First consider a point A at a distance x from the charge, that is plus Q, right? So here the Q naught value is equals to 1 coulomb. That means we are bringing the unit charge 1 coulomb, right? So we are moving the charge Q naught, so up to here. So small displacement, that is B, right? So this displacement we taken as dx, right? So by applying the external force here, so we are bringing the charge from infinity to the point A by applying the external force here. So from here to here, the charge is displaced by the amount dx, right? So from that, first we find the work done, that is small work done dw, that is equals to force into, right, force into displacement. So this is from the definition of the work done, right? So here we have the plus q, and here also we have the q, that is value is 1 coulomb. So from the Coulomb's law, dw is equals to 1 divided by 4 pi epsilon naught q into 1 divided by, so here the value is, the distance is what, x square, right? So from this charge to the point A, right? So the displacement is, we taken dx. So which dx it is? It is opposite to that of the external force. Sorry, electric force, that is Fe, right? So for that we have taken the displacement as negative, that is minus dx, right? So we get dw is equals to minus 1 divided by 4 pi epsilon naught into q divided by x square into dx, right? So we need the total work done to bring the charge from infinity to this point P, right? So we are going to bring the charge 1 coulomb from infinity to this point P. So we have to integrate this one, right? So the total work done W is equals to integration from infinity to this point is at a distance R, right? So we are integrating the work done dw, right? So here we are written dw, right? So now we know the value of dw, substituting here, that is from infinity to r minus 1 divided by 4 pi epsilon naught q divided by x square into dx, right? So here the values 1 by 4 pi epsilon naught into q is constant, so taken outside, minus 1 divided by 4 pi epsilon naught, or here q divided by 4 pi epsilon naught, again integration from infinity to the r, that means limit. So this one is the initial starting limit, this one is the ending limit. So starting is from infinity and ending is at r, right? So this x square goes to the numerator, it becomes x to the power of minus 2 dx, right? So we know integration of x power n dx, that is equals to x power n plus 1 divided by n plus 1. So now applying here minus q divided by 4 pi epsilon naught x to the power of minus 2 plus 1 divided by minus 2 plus 1, so limit infinity to r, right? So again here work done is equals to minus 1 divided by 4 pi epsilon naught into, so x to the power of minus 2 plus 1, we get x power minus 1 divided by, so minus 2 plus 1, we get minus 1, so infinity to r, right? So w is equals to minus and minus get cancelled, we get work done is equals to 1 divided by 4 pi epsilon naught, so x power minus 1, we return 1 by x infinity to r, right? So by applying the limits 1 divided by 4 pi epsilon naught, 1 divided by r, first we are applying the upper limit 1 divided by r, then again minus 1 divided by infinity. So we know 1 by infinity is 0, so this term becomes 0, right? So the work done is equals to 1 by 4 pi epsilon naught. Here we have got 2. So here q divided by r, right? So this gives what work done, bringing the charge from infinity to the point P, so that is at a distance r. So from the definition, bringing the unit charge, right? So bringing the unit charge, so that work done is equals to the electrostatic potential, right? So that means V is equals to W, right? So V is equals to, we know the W here, 1 divided by 4 pi epsilon naught into Q divided by R. So this is the electrostatic potential final relation, right? So very important relation, that is electrostatic potential, right? So first we have considered one point charge which is placed at the origin, right? So we are going to find the work done. So that's why we are bringing the charge from infinity to the point A which is at a distance x, right? So by applying the external force to bring the charge from A to B, then work is done. So work done is equals to, we know the force into displacement. So this force is the external force. So that external force is always opposite to that of the applied, that is electric force, right? So the displacement is opposite to that of the electric force, right? So electric force is from left to right, but the displacement is from right to left, right? Or we can write the direction like this. So those two are opposite, hence we taken minus dx, right? So again, we get the small work done here. To find the total work done in bringing the charge of 1 coulomb from A to P, right? So that's why we are integrating. So we know W is equals to, we have the limit starts from infinity and ends at a point R, right? So from infinity to R, we know dW. So substitution and simplification, we get V is equals to 1 divided by 4 pi epsilon naught Q divided by R, right? So here, if we observe here, 1 by 4 pi epsilon naught is constant and Q is also constant. That means V is proportional to 1 divided by R. So if we plot the graph for V versus R, so the graph is like this, right? So in the last chapter we discussed the electric field. So E is equals to 1 divided by 4 pi epsilon naught, same Q divided by R square, right? So this is the electric field due to the point charge, right? So 1 by 4 pi epsilon naught and Q. So all these terms are constant. So we have E is directly proportional to 1 by R square. So here the potential is 1 by R and the electric field is 1 by R square. So if we plot the, so this is for the potential. If we plot for the electric field, so this will be the current, that is E, right? So V is proportional to 1 by R, E is proportional to 1 by R square. So we need to remember this one, right? So both graphs are same, right? So because these are exponential, 1 by R and 1 by R square, right? So this is the curve for the potential and the display distance R. So if we increase the distance, so potential further goes on decreasing, right? So this is for the point charge. So if we have the many number of the charges as similar, that is potential due to number of charges, right? So as we discussed earlier in both force and also in electric field. So we have so many number of charges. We have Q1, Q2, Q3, so somewhere here Q4. So at this point we are going to find the electric potential due to the system of these four charges, right? So P is the point where we are going to find the electric potential. So potential is on the displacement, right? So here R1P, R2P, next R4P, and here R3P. So that is by the, again by the superposition and so on up to Vn. right? So we know here the terms V1, V2, V3. So from all these terms, the common term is 1 divided by 4 pi epsilon naught. So remaining is Q1 by R1P plus Q2 by R2P and so on up to Qn by Rnp, right? Or we can write this one in general, V is equals to 1 divided by 4 pi epsilon naught summation of I is equals to 1 to N, that is Qi divided by Rip. So if we substitute I is equals to 1, then we get Q1 divided by R1P. So next if we substitute I is equals to 2, Q2 divided by R2P. So this is due to system of charges, right? So this is about the electrostatic potential. So electrostatic potential is defined as the work done per unit charge. So simply we say V is equals to W by Q. So this gives the relation of the electric potential, right? So electric potential is equals to work done per unit charge. So always this charge is always equals to 1 coulomb, right? So unit charge is nothing but 1 coulomb, right? So in case of potential energy, we are bringing a charge, right? So it may be 2 coulomb, 5 coulomb, any value, right? So that one we call as the potential energy. So in both the cases, we are bringing the charge from infinity to that point. So right, so here we going to calculate the potential means at this point we are bringing some charge from infinity to this point. The direction may be, that means the path may be any. So I can bring the charge either like this, or I can bring in the straight way, or I can bring like this, right? So here it is independent of the path because the Coulomb's force is the conservative force, right? So due to the conservative force, it is the path independent, right? So that's why it is written in the direction either like this straight line or curved like this, right? So this is very important relation, right? So we need to don't confuse with the three formulas: force, electric field, and potential. So one more will become, that one is the potential energy, right? So these are the four important relations, right? So Coulomb's force 1 divided by 4 pi epsilon naught Q1 Q2 by R square. So here we are going to take only the magnitudes, not the signs, right? So electric field E is equals to 1 divided by 4 pi epsilon naught Q divided by R square, right? So again comes to potential 1 divided by 4 pi epsilon naught Q divided by R, right? So all formulas looks like same, right? So here there is a force between two charges. So electric field is equals to force by charge, right? So electric field is equals to force divided per charge, right? So next potential V is equals to work done per charge, right? So we can write F is equals to Q into E. In the same way, the work done is equals to Q into V, right? So these are the simple formulas. And here in force and electric field we have the squares in the denominator. Here in the potential we have 1 by 4 pi epsilon naught Q divided by R, not R square. So one more is potential energy U. So in the next class we are going to derive this relation. So here we have 1 divided by 4 pi epsilon naught Q1 Q2 divided by R, right? So here these two relations are for the potential and potential energy. So V is potential, it is in volt. The unit of potential is volt, that is joule per coulomb, right? So potential energy is joules, right? So these are the four formulas from these two chapters are very important. So don't confuse with these formulas, right? So here force is a vector, right? Electric field is also a vector. So potential is a scalar. So here we are not going to find any direction like this, right? So we are going to simply add the potentials due to Q1, Q2, Q3 and so on, right? So the method is same, right? So in the next class we will continue with the dipole, right? Thank you. So another doubt.